First of all, thank you for the invitation from the lab, and it's a great pleasure for me to be here to talk about different topics about my research here, continuum percolation for Boolean models, and during the mini course percolation, stochastic geometry and statistical mechanics, mixed problems, and but for other things. So today I would like to give this talk about continuum percolation. And to present, of course, a survey, and not too much technical, just to give the main results in this direction. So maybe you heard a lot of time problems about percolation, but in general, percolation is for discrete model. And for example, classical in Z2, for the site percolation, we consider so Z2 here in the discrete points here, and now we fix the parameter P belongs to 0, 1, and we independently open the site with probability P. So this site is open with probability P. So for example, this one is kept. This site is closed with probability 1 minus P, and for example, it's closed. And all is independent, so we have a feature like this. Okay. And now so imagine an infinite volume models, of course. And percolation means is there exists an infinite connected graph. So for the moment, it's not a graph. So you connect the points if there are neighbors. So for example, this one is connected, not in the diagonal, connected. And so imagine like this, an infinite graph, so connected, so there are connected components, and percolation means the existence of an unbounded or infinite connected components. So this kind of models here is for a first example of the description of material. So it's a microscopic description, and we are interested by macroscopic property, which is, for example, the percolation. And this is a site percolation, and there exists also the same problem with bound percolation, and it's still related on Z2, but here like a grid, we consider a grid here. And now with probability P, okay, with probability P we decide to keep or to erase an edge here. So for example, we keep it, we erase, and so on. And so we obtain finally the same kind of graph here with edges. And percolation means the existence of unbounded graph. It is in the discrete setting for the percolation. And of course, sometimes we are interested with more complicated or more continuum model. It's the second term. And continuum means models from stochastic geometry. So we want to relax the assumption of well-structured grid or lattice. And we want a continuum model. It's what we do in general stochastic geometry. So we want point. We don't know exactly. It's random. And now, so the points are random, and the connections are also random. And the main model, the principal model in stochastic geometry, is the Boolean model. For that, at each point, we consider a ball with random radii. So, for example, like this, and the radius, the radii are independent. Sometimes big ball, small, like that. So we need also an infinite model. So we imagine an infinite collection of points in the plane, for example in R2, but we can do it in the RD. bars with. So we can imagine this kind of models is a description of a sponge. So imagine a sponge with holes inside. And so we put a number of holes. And the holes are not the same, and they are random and morally independent. Okay, and now we're in this setting. It's a microscopic description. You imagine an infinite model like that. And after that, the sponge, what is important is what is the behavior of the water. So we put water here. I know it's not blue. Okay, this one is blue. And we are interested in the sponge, the permeability of the sponge. So in the infinite volume model, is the water able to flow inside the structure. Okay, so it's directly related to the percolation of this model. So we consider the union of bars, and we are interested in is there exists an infinite connected component in this structure. So this kind of model is really used in material science for the permeability, conductibility for the electricity in material, or in communication, this is the point and the size of the connecting between people, for example. So you have a connection between people. So in stochastic geometry, this model is really popular. So it's called Boolean model. And the percolation for this kind of model is quite important for a lot of application in biology and material science, telecommunication, and so on.
I never understood this name. Why is Boolean?
Boolean, so in algebra, Boolean is 1 or 0. Yeah. So here, pick a random point, is out or inside the model. It's what it's called Boolean model. So it's, but it's not algebra at all. And it's just inside or inside or outside the model. It's what it's called like that. So we can use other kind of grains. It's called grain, balls, or square, or any convex sets. But for simplicity, I decided to present the Boolean model with balls. And we will be interested in the existence of infinite connected component for this kind of model. So we see for stochastic geometry, a lot of application, it's really important to use a continuum model with points and not only a grid, because for the holes or for communication, there is no reason for the people are exactly on the grid and they are well sparse in the space. So it is a general picture of the talk. To be more precise, I have to give a precise description of this model. So the first thing is to find a good model for the points. And this good model is Poisson point process. So maybe for a probability guy, it's quite obvious what is it, but I just give a definition for everybody. You have not to know anything. So we want to find the best way to produce an infinite collection of points in the space, with a good repetition in the space. How to do that? So we fix Z. It will be a parameter which is the number of the mean number of points per unit of volume. So the mean number of points per unit volume. So you keep in mind this parameter. So if you consider a box, so we are in RD. If we consider, sorry, my picture is indeed equal to a box 1, 1. We want a model for points, for random points, such that the mean number of points in this box is exactly Z. Okay? How to do it? We start with any finite bounded set in RD, Borel set, of course, with the Lebesgue measure between 0 and no, finite. This is lambda, 1 lambda, for example. So first we have to decide how many points there is inside here. So there are a lot of things to do. We have this constraint here, but we put inside the number of points, and lambda will follow in distribution the Poisson law. With parameter, it's quite easy to find it because the expected number is exactly the parameter. And so, with respect to this rule, we have to put exactly z times the Lebesgue of measure of lambda. So we put this number of points. It's random, and as the expectation is exactly this quantity. So it's okay for this rule. And now, given the number of points, the points are independent and uniformly distributed. So it's quite easy distributed to sample. So for example, the number is 3, you put 3 points randomly independently. Okay? So it's quite easy. So the question, this construction is quite clear if you want a random uniformly distribution. Why is that? It's because the following property, if now I consider 2 boxes inside here, lambda 1, lambda 2, and I now consider the restriction of this process in this box here, it's exactly the same construction than here. The number of points follow a Poisson distribution with parameter z, the Lebesgue measure of lambda 1, and the points are uniformly distributed and independent. So the construction is consistent. And this box, what happened here and what happened here is independent. So this part and this part is independent. So now, when I have the construction here, how to do in a larger box, I consider another box here. I do the same, independently of that. And so, finally, what we can do in the partition of the space, the full space, and we do the same construction everywhere. So we obtain, finally, an infinite connection of points, and with the property that this part and this part are independent. If we consider this joint set, what happens in this set and this set is independent. And the description is exactly this one. Okay, so now we have a process, it's a Poisson point process, it's this one. Okay, so the point here are just described by a Poisson point process. Okay, now it's quite easy to consider a collection of independent variables. So your point process N is an infinite collection of points. We can give, for example, this description. So it's infinite, yeah? Almost surely it's infinite. Now I consider RE, independent variable, IID variable, on R plus. It's for the law of the radius here. I put for each point a radius. And the law of each point is distributed by a law I call Q. So Q now, for the rest of the talk, is the law of the radius. Okay, and now the Boolean model is just defined like that. It's the union of closed ball, central xi with radius fi. Okay, this is a description of the Boolean model. Okay, Maybe I keep this blackboard like that and I write it now. Okay, the first interesting thing we can do is what is the space, what is the fraction of the space which is covered by this Boolean model. It means, so we have a proposition here. We called f vol, I explain why in a second. So I keep lambda include in RD. With always this assumption. The Lebesgue measure of lambda is positive and not equal to infinity. I consider the expectation of the volume of the Boolean model inside the window lambda. And I divide it by the volume of lambda. I'm not sure it's clear what I do here. I consider just a window, lambda, and this quantity lambda L in intersection with lambda is just this part inside lambda. I consider the volume, the Lebesgue measure of this quantity here, and I divide by the Lebesgue measure of lambda. So it's just the expectation of the fraction of the space here which is occupied by the Boolean model. We can prove that this quantity by stationarity argument is just equal to the probability that 0 belongs to L. It's just equal, fix the point 0 somewhere here, and just consider the probability such that 0 belongs to L.
For any lambda, big lambda.
Yes, for any lambda. In fact, this quantity does not depend on lambda. It's what it claims, this equality.
But it's a theorem.
Yes, it's not so obvious, but we can prove it. It's not so difficult to prove that. But it's exactly what I would like to say. So this quantity does not depend on lambda. And we can compute explicitly.
In any dimension.
In any dimension. It's 1 minus the probability 0 is not in lambda. So it's obvious. And this quantity we can compute explicitly because it's not too complicated to compute the probability such that the Boolean do not cover something. It's not only 0, a compact set, we can compute it. So I give you the formula. It's exactly exponential minus z Vd expectation over Q under Q of Rd. So I just explain exactly what are the different things. So we have an explicit formula for this part here. And so Z is Z. Vd is the volume of the unit ball. So Vd is just the Lebesgue measure of the ball with radius 1, so in dimension d. So, okay, you know the formula, but I just write Vd. And this quantity is a d moment of R under the law of Q. So it's just the expectation R to the power d, Q dr. It's just a d moment of Q. Okay, so we have an explicit formula, so it's quite interesting and pretty beautiful result. And I called it F vol, the volumic fraction. It's the fraction of the space which is occupied by the Boolean model. It's clear by this definition, and it does not depend on lambda.
Is this straightforward by the inclusion-exclusion formula or something more?
We cannot use this formula. It's quite surprising here. Of course, we have in mind if you want to compute the area, we have to use exclusion formula, but it's too much complicated. So it's completely different, this approach. It's a probability approach, completely different. But you're right, it's quite surprising this expression is so simple here because the exclusion formula is complicated, but it is really simple here. Okay.
Who invented this continuum model?
Sorry?
Who invented this continuum?
Continuum model was, it's quite old. I don't know exactly, it's 60s. That comes from stochastic geometry. I don't know exactly. Maybe I prefer to not give a name because it's quite. But I will try to find precise original name of this model. Okay, so we have this formula. So we have a first corollary interesting. If expectation of Q RD is equal to plus infinity, so imagine a law Q without D moment. So the expectation of R to the power D under Q is equal to plus infinity. Huh? It's a positive random variable, so we can define that like that. So what you find here, this quantity vanish and you have 1. But if you have 1, all the space is covered. So we obtain L is almost surely equal to RD. So if the law of radius don't have D moment, all the space is covered by the Boolean model. It's quite complicated to see that, maybe just because it's possible there is no points here, but what it's claimed by this result is somewhere, maybe far away, there is a ball with a large radius which covered any point. So it's what is claimed by this result. So now, in the following, of course, it's not so interesting this case because all is covered, no percolation occurs because only in an unbounded component. So now, an assumption is this quantity is finite. Okay. Okay, now, so we are in this regime now, and so the model is complicated like that, with a connected component, with holes and so on. And so we are interested by the percolation. I prefer to write precise definition. We say L percolates if L contains an unbounded connected component. Okay, so we are looking. We have a proposition not too complicated. It's this probability L percolates is necessarily equal to 0 or 1. Or 1. So two ways to see that. This event, L percolates, is a shift invariant. If you translate the model, this event is the same. And so, like the Boolean model is ergodic, you can prove easily so any shift invariant events are the property 0 or 1. So one way to see that. Or another way to see it is the 0-1 law of Kolmogorov. This event does not depend on a local modification. If you change your events locally, if you change the Boolean model locally, this event doesn't change. Because L percolates means there exists somewhere an unbounded connected component. If you change locally your model, this connected component exists still or not, if it was existing or not.
If you cut by changing something.
But if you cut an infinite connected component, we will have two infinite or one infinite component. There exists also. It's not related to the number of connected. At least one. If L contains, it's not only say at least one, but finally we can prove it's only one. No? So this event is equal to 0 or 1, and we can prove if we consider this probability like a function of z. And you change the model, if you consider this event like a function of z, the Boolean model for the parameter z, it's not so complicated to see that this function is increasing. If z is increasing, there are more balls, and the percolation is favored in this when z is increasing. So this function is increasing in z. So the general feature of this function is like that. So at the beginning, of course, for z equal to 0, if z is equal to 0, so I exclude it, but imagine equal to 0, no points. So no percolations of this quantity is equal to 0. And it's increasing and is equal to 0, 1. So finally, it's like that. Okay. We have some things not clear here. In certain setting we know if it's equal to 0 or 1, but not in any case. So we don't know exactly what happened here. But in any case, we have a jump at a point which we called Z star. And Z star is the intensity threshold. Before Z star, we do not percolate. After Z star, we percolate. And in Z star, we don't know exactly what happened. So, okay. But at this stage, we don't know exactly if Z star is really positive. Because maybe, okay, in 0 it's clear we do not percolate, but maybe just for a small z, really small z, we percolate. Because somewhere there exists an unbounded connecting phenomenon. So it's the first question. And are we sure that for z large enough we percolate? So it's not sure at all also that Z star is finite. So it's the two main questions in percolation theory, in particular in Continuum, about how is Z star finite, not equal to 0, and so on. So I would like, we will talk about this question in a minute, but before, maybe I can give you a kind of how to approximate Z star. If I give you this model, I give you a log Q. Can you give me approximately what is the value of Z star? It's just an approximation, an idea to find an approximation. It's just an exact result. It's just to, for example, for simulation, when you're trying to find exactly the Z star, we can start from this value that I will give in a moment. What is the idea to find approximation of Z star? In the bond percolation, for a lot of models, if this model is self-dual, so it will be the case for the bond, the percolation threshold is exactly at the point where the model are the same for the dual. But we need the self-duality of the model. But here, for the Boolean model, of course, the Boolean model and the complementary are not the same structure. So we cannot use this idea to find Z star. But we can try to do like it was the same. So we can just to have a look about the topology of the Boolean model, and we say the good equilibrium will be when the number of connected components is equal to the number of holes. Because the Boolean model is balls, is structure, and we can say the equilibrium is when the number of connected components and the number of holes are the same. And so you can do it that with the Euler characteristic. So, so I recall the Euler characteristic is just equal to the number of connected components minus the number of holes. And this functional is defined, for example, for a union of convex, a finite union of convex. So we can use it. You can use it for the Boolean model and prove also it's true in dimension 2. The expectation of the Euler characteristic of the Boolean model inside the window lambda divided by the volume of lambda okay. This quantity does not depend on lambda like before for the volume fraction, and it's exactly equal. So I have a formula a little bit more complicated, but not so much. It's z times 1 minus z by expectation over q under q of r times e square here, sorry, times exponential minus z p exponential over q r2. So the pi here is just the volume of the unit ball in dimension 2. Here the square is inside the expectation, here is outside the expectations. And we have this formula for the mean. It's the mean Euler characteristic of the Boolean model. So it's explicit. So it's quite a nice result also. And so give a picture of this function. So we have 2, 0 here and 1. So the first is here, and the second one is for the graph. The function is like this, and this point is the root here. So 1 over p expectation q r2. So we are in dimension d is equal to 2 here. So we can do the same in dimension d. It's a bit more complicated, but we can do.
But this z star depends on d, on the dimension.
Yes, of course. that star depends on d, yes, of course. And we have an asymptotic when d is large. But yes.
You have asymptotic?
Right, yeah, when d is large, but for d small is unknown. Yeah. Nobody knows the value of that star. But in asymptotic, when d is large, we can compute an asymptotic. It's going to 0.
Going to 0.
Yes. And here, this point, so just to have a feeling of what happened, here at the beginning where z is increasing, so here it's z, okay? Yes, it's z. And here is the value here of the mean Euler characteristic. So at the beginning, when z is equal to 0, there is nothing in the space. When z is increasing, some balls appear, and the number of connecting components is increasing, and number of holes not really. Only connected component appears. At a moment, we add new balls, and we create more holes than connected components. So we are exactly here. When you add a ball, you have, for example, like that. We add a new ball here, so we create a hole here, but we don't change the number of connected components. So at this stage here, when z is increasing, you create more holes than connected components. And we go on like that. And when you are here, the number of connected components and the number of holes is equal, expectation, the mean value. is equal. And so we can, it's not an exact result, but we can say at this stage the model is quite dual. The number of connecting points and the number of odds are the same. And so you use this point like a first approximation for Z star. But it's not Z star, but it's the first approximation. Okay. So for example, in the Boolean model, in dimension D is equal to Q is a Dirac 1, it's just non-random radius fixed equal to 1. So we have more or less Z star which is equal to so 1 over P. So it's not the good value. We know it's not the good value, but it's not so far. By simulation, we can see it's not so far. But. Okay, so it was just here this thing so to show you how to find a good first approximation of Z star, and a lot of people are still working on this direction to find a way to capture Z star from the Minkowski functional. Only this one, but the perimeter, the volume, or the Minkowski functional. But it seems to be a bit complicated because these functions are really local. It's a local function. It's additive functional. And the percolation property is more global. So it seems difficult to obtain a result in this direction, but I try to find approximation. Okay. So come back now to the problem about the value of Z star. So we have the first proposition. It's quite easy to have Z star not equal to infinity. In the general setting, so if Q of 0 is smaller than 1, the opposite is just all the mass is concentrated on 0. Of course, if all the mass is on 0, the balls are reduced points and the percolation cannot occur. So this assumption is quite natural. In this setting, we have Z star is finite. So it's not too much complicated to see it, but I don't really have the time to give a small proof, but it's directly relative to the discrete percolation. You can use a result in discrete percolation to prove this result. Okay, so the main problem is not this one. The main problem is this one. When Z is small enough, is it possible to have no percolation? The percolation do not occur if Z is small enough. It's a main problem here in continuum percolation, and it was a problem which was unsolved since recently, but I will give you exact result here now. So, what about this question? So we have a first important result, which is the following one. The probability that L percolates is equal to 0 is equivalent to the probability that the connected component of L union the ball centered in 0. So add a ball in 0, and we just are looking about the connected component of this ball containing 0. Is unbounded with probability 0. So just let me explain with a picture. So consider here the Boolean model. Like that, you have somewhere 0. And we claim that the probability that L percolates is equal to 0, no percolation, if and only if we add a ball in 0R, so R is random with the log Q, so add a new ball in 0. And now we look only the connected component of L with this new ball. So we now have a look about the connecting component of this ball from 0. So this connected component is this one. Is unbounded with probability 0. So it means it's enough to have a look about this connected component to understand if the Boolean model percolates. If this probability that this ball is connected to infinity with positive probability, it ensures this probability is equal to 1. So we have an equivalence between this one. So how to imagine to have a good representation of this result is just when you add a ball here, it's like we choose randomly a connected component. It's a typical connected component is this one, typical one. So if the typical connected component has a probability 0 to be infinite, so globally no percolation occurs. Percolation do not occur. So it's an equivalence here. And so this assumption, I call it 1. This one, I call it 1. And it's sometimes easier to deal with another one. The other one is called 2. And it's the number of balls in this connected component is finite. And the other assumption is the expectation of number of balls. So the expectation of number of balls in the connected component of L union B0R containing 0 and we consider the expectation of this number, and this expectation is finite. So here it's the number of balls, number of all balls in the connected component from 0 is unbounded, and here the number of balls in the expectation is finite. So this one can be the number of balls in this connected component is finite with probability 1, and this one the expectation is finite. So we have clearly 2 implies 1. And okay, sometimes these 1 and 2 are equivalent, but it's only when the radius is uniformly bounded. And so if the radius, if Q has a compact support, 1 and 2 are equivalent, except it for Z is equal to Z star. So we can use like a fresh. But so I don't want to give too much detail, but I would just to give you 2 main theorems about this. So the first one. So Mr. Roy maybe it's closer, it's earlier. It's a 94. Claims if Q has a 2D moment, this thing is equivalent to exists Z tilde such that, so strictly positive, such that for all Z smaller than Z tilde, 2 holds. And it's an equivalence. So if Q has a 2D moment, so for Z small enough, the number of balls in the connected component, the expectation of number of balls in the connected component is finite. So the connected components are finite. And percolation do not occur for Z small enough. But we have more here. We have the expectation of number of balls in the connected component are finite. And it's an equivalence to have a 2D moment for Q. So for a long time, so maybe 12 years, it was the only one way to prove that the percolation do not occur for Z small enough. But for the problem is what happens if Q don't have a 2D moment, but for example a D moment, like the basic assumption. And for that we have a second theorem with my colleague, proved by my colleague Dereudre in 2006. And he proved is Q has a D moment it's an equivalence between there exists Z tilde positive such that for all Z smaller than Z tilde 1 holds and 1 is equivalent to the percolation, to the no percolation. What it means, so with these two theorems we have exactly what happened. If Q has a D moment, like it's a basic assumption, for D small enough, 1 holds, and so the percolation do not occur. So for Z small enough, the percolation do not occur. But if Q don't have a 2D moment, it's impossible that this 2 holds for Z small enough. So what we find finally, it's a kind of global result. If we are exactly in this situation, and this setting is completely different in discrete model. So it's what I point out this result. Imagine a low Q such that this quantity is finite, but not this one. So Q has a D moment, but not a 2D moment. Okay, so we can imagine easily. So in this setting, it happens the following things. There exists Z tilde positive such that okay, it's clear, it's come from here. So the percolation do not occur for Z small enough, but, so I have to write it quickly. So expectation number of balls in connected component, so the expectation of number of balls in each connecting component is equal to infinity. So it's quite a surprising result. Which is impossible in discrete model. For the lattice site or bond percolation, this kind of situation can appear only in Z star at the threshold. At the threshold it's possible this situation can appear, but not for Z smaller than Z star. Because for Z smaller than Z star, the size of the connected component is exponentially decreasing. So the expectation is finite. But not in this setting. So it's quite unusual result, which appears only in this setting of continuum percolations. So it is the reason why I would like to point out this nice result. Okay, it's almost finished, but I would like to finish with a conjecture. So it's always nice to have a conjecture because it's I can try to prove it. And I'm working on this conjecture, but I can share the conjecture, of course. It's a quite old conjecture. It will be quick. So we call F vol is the volumic fraction of occupancy of the Boolean model. It's equal to 1 minus exponential min z vd expectation order q r to the power d. And now we can compute it at the value z star. And this quantity depends of q. So I call f vol star of q. It depends on the law. It's exactly this quantity here. So what does it mean, this value? It's called volumic fraction of percolation. It's clear because it's exactly the volumic fraction of the Boolean model at the value of the threshold Z star. So it means it depends on the log Q. Fix the log Q. So we have a Z star with a percolation threshold, and we compute this volumic fraction at Z star. So it represents exactly what is the fraction of the space we have to cover to ensure the percolation. Okay, what is the fraction of the space you have to cover to ensuring the percolation? Okay, so there is a long time conjecture about that. The first one is, okay, maybe the first thing to notice is that thing. So fix the radius equal to 1, consider the fraction for the occupancy, and it's clearly equal if you change the value 1 by, for example, 2. Because we change the size of the radius, but we are just interested by the fraction of the space you have to cover. But by rescaling argument, this fraction of the space you have to cover does not depend on the scale. So if you change the scale, if you are looking at the model closer or further, that does not change the volume fraction of occupancy for the percolation. So it's scale invariant. And the first conjecture was, okay, if it's constant for the constant law, maybe does not depend on the law. So the first conjecture was this function is constant. So volumic fraction for percolation does not depend on the law. It was a kind of universal property for the percolation, but it's false. And Mr. and Roy in 2000 gave a counterexample. So the first conjecture. The second conjecture is okay. It seems to be so the counterexample don't give something which is bigger than this one. And all the examples as a simulation seems to show that this one is a smaller one. So the second conjecture claims conjecture 1 and 2 that the minimum value under the law Q of F vol star Q is exactly the volumic fraction, percolation volumic fraction for the deterministic law. So it means the conjecture claims the minimum fraction for ensuring the percolation is obtained for the deterministic law of radius. It's the deterministic law of radius which ensures easily the percolation. And it's false also. And it was recently, in 2012, Dereudre and Marchand. 14, it's not really definitively accepted. Give an example, but for D large. So it's quite larger than 19. So for D large enough, they find a law, Q, such that the percolation volumic fraction of this law is smaller than this one. Just by simulation, this one is more or less, it's obtained by simulation. With deterministic radius, you have to occupy 2/3 of the space for ensuring percolation. And so they find, so in dimension 2.
And this result is by some computation or by sort of covering?
This one?
Yeah.
No, it's an exact result. It's they give an example, they find a law, they compute an asymptotic when D is large.
Yes, it is.
It's an asymptotic.
So they find the law and make a computation, but they don't do any coupling with them.
No. They give a precise law, and by asymptotic when D is large, when D is going to infinity, this equality is false for D large enough. So it's an asymptotic result for D large, but the conjecture, which is still not active, it's that true, because the simulation seems to show that. So this conjecture is true for D is equal to 2 or 3, or maybe more, but not for D large. So it's proved not true, but for D and 2 and 3, the conjecture is still active. And it's quite important because in material science or in general, it's important to know which kind of law you have to put on your balls or the radius to ensuring easily the percolation. So it's quite an important result in applied science or in theoretical also, but not only the theoretical result. So it's a very nice conjecture, and we are working with my colleagues on this conjecture. So we are not very far to prove it, but it's not done. So it's still a conjecture. Okay, so I finish with this conjecture, and I thank you for your attention.
Any questions?
For the fifth case, if you had a lattice at D, you could say that, okay, if any point I have a coin and do it open or close, yeah? But you also can say that there is a radius.
Yes.
And that it connected somehow.
Yes, I saw recently a paper about that. Probably the same kind of feature appears here, or this kind of model. It's really due to, it's not really due to the freedom of the points, but by the large range of the balls. So if you consider maybe the models we talk about with this kind of radius, maybe this kind of result is true too.
More questions?
So, and you said this corollary is specific because for Bernoulli graph percolation, so this is not true.
Yes.
And this is obvious, or?
No, it's not. No, it's not obvious. But for Bernoulli percolation, for P smaller than P star, the size of the connected component has an exponential decay. It means the size of connecting component is bigger than n, with probability smaller than exponential minus n. And so the number of sides in a connected component admits a finite expectation with this exponential decay. So, and here it's not the case, because for any z smaller than the z star, so of course the connected component is finite, but the number of balls in the connected component for any z, the expectation is infinite. So it's quite surprising, this result, but it's proven.
More questions? Are there any examples of the law Q for which you can compute these stars explicitly? Or there are none?
No at all, no.
Just
it's unknown.
Very special Q?
But in the discrete percolation for Z2, we know the value of a P star only for some models when you have, for example, symmetry, duality of the model, and so on. For example, the bond percolation in Z2, but it's rare. More or less, it's rare to be able to find the Z star or the P star. And here, I know for any model, we don't have the value of Z star. Only by the
F star, right?
only for approximation.
And could it be 2/3?
It's by simulation.
It's by simulation.
It's by simulation.
0.66. Yeah, but could it be?
No, it's not 2/3. No. Because the simulation is better. You can have but I don't know the value. But it's better, and in the error claims it's not 2/3. So it's different. It will be nice, but it's not.
And do you know stuff in the parabolic geometry?
On topology?
No, just on parabolic geometry. If you have
Yes, I know there exists result, but I don't know this question at all. But I think there are results also. I think the Boolean models is defined also in this kind.
Yes. It's totally defined on the plane.
Yes, and it's to die, and it was to die. Yes, yes, it was to die, but I don't know the result. I think we can have a look, but I can say nothing interesting now.
More questions? So let's thank the speaker again.
Thank you.